The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Thank you for joining us today. My name is Emily Kuda, and I'm Percona Senior Manager of Marketing Programs. We're going to get started in just a moment. For those of you that are joining us, can you raise your hand using the hand icon located in the control panel to let me know that you can hear me? Great. Okay. So next during this webinar, you're going to be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we'll take time to answer as many questions as possible. Those that aren't addressed will be answered in a follow-up blog entry on Percona's database performance blog. In addition, a recording of this webinar will be made available to everyone within 48 hours or less. So with that said, I'd like to thank you for attending today's webinar as we talk about running MongoDB in production. This is part 2 of our series, presented by Percona's Senior Technical Architect, Tim Valancourt. Take it away, Tim.
Hi, everyone. Let's get started. There's a lot to cover in this second piece. If you've seen the last slide, the last piece, you've already seen the slide. I'm the architect for MongoDB at Percona, and I've worked with a lot of other techs. Just something to start with. The agenda today we'll be looking at architecture and high availability. Those two kind of go hand in hand with Mongo. Hardware, tuning Mongo, and tuning Linux. So architecture and high availability is all about setting up your deployment for safety, really, or really just keeping your application alive. The main way Mongo pulls this off is replication. It's very similar to how MySQL works with masters and slaves. In Mongo, it's called a primary and a secondary. Those terms were in the first piece of this webinar. If you want to go back to look at some of those terms. So the replication is asynchronous, but write concerns in Mongo allow you to, from the application, pretend the replication is synchronous. So you get the kind of performance of asynchronous replication, but when you really think something's important, you can use something called a write concern to say, I'm going to wait until many members in the replica set have acknowledged that change. So you get both the performance and the flexibility. That's similar to perhaps Cassandra, where you can say how many nodes you want to replicate to, but you actually are waiting for that change to go to all of them synchronously. So this is based on the oplog and replication, basically, when you use write concerns. You can have a maximum of 50 members in a replica set and 7 voting members. And voting, I explained briefly in the last piece of this webinar. Same with the oplog here. Architecture is important. This slide is a really important one, and just this news screen grab on the right of this happened many years ago now, in 2011, when Amazon lost an entire piece of their US East region. People who set up their production in a single availability zone, that was the one that went down, were heavily affected, where setups that were in many availability zones and regions were okay. So I generally recommend that you always just put a replica set member if you have 3 or 5 in different availability zones. The best way that I know is 3, because Amazon almost always has an A, B, and C AZ. But for other regions, I can't say for sure if there's going to be 5 A, B, C, D, E or not. But just make sure it's in as many places as possible, so that if there's an issue with that building, which has happened in this case, it was a bird hitting a telephone pole, I believe, that took out the entire piece of a large piece of Amazon that Mongo could actually stay alive when set up properly. So think about that. Also, I recommend putting a hidden secondary node in a different region for backups. So a hidden secondary can have as much delay as it wants. The application doesn't see it as a list of nodes to read from, so the application doesn't ever read from that, and it also can't become the primary. So it's just a great node to have in another region marked as hidden for backup reasons and disaster recovery as a cheap disaster recovery option. Hardware is important to think about with Mongo. There's a concept that I call the mainframe concept that's kind of pre-2000, spend a lot of money on a server versus the commodity, which is have a lot of cheap, slower servers or relatively not as fast servers. In this slide, we'll just talk about the past, where you can see in this picture, this is a very large room size server that was probably very expensive. It's a mainframe where many use cases were probably put onto that. The problem with that is you probably need a very expensive hardware, probably an expensive license if you're using a server that was focused to use few nodes. And scale up can be difficult because if you only need half of another mainframe in resources, you either have to buy a whole new mainframe or none. Also, in HA perspective, when it rains, it pours, I like to say, because if you only have 3 very massive horizontally scaled servers versus maybe 12, sorry, I got those wrong, 3 vertically scaled servers versus maybe 12 horizontally scaled cheaper servers, the HA is affected drastically because losing one node is a 33% hit to your overall capacity. Mongo was designed to use, like I've alluded, cheap servers, and this is kind of the new era of computing that I feel like Google or Facebook started. When I was starting off in the industry, I thought Google was probably using some very big, expensive servers, but it was quite the opposite. They were using some very cheap Celerons, I believe, at the time when I was looking many years ago, in very cheap commodity servers, usually without a full case. In this image, there's a full case, but I believe Facebook's server is just an L bracket of steel with some cheap components on it. So the key here is things in this kind of new era of thinking is hardware is a more expendable thing. If it breaks, you throw it out and you put another cheaper server in its place instead of focusing a lot into one place with very expensive hardware. Block devices is great to talk about with hardware because we're using a database that stores stuff. Block devices are one of the big things to worry about. You can worry a lot about the RAID level, but with the last slide I just talked about, that kind of is counterintuitive because I just said you don't really need to spend so much money. It's kind of a balance. If you do want to have RAID levels in a host to make sure that your disks are redundant, you can do that, and that will make sure that a single node is redundant. But we can also talk about it later that there's a trade-off that you can just have more replica set members with possibly without RAID as another way to spread the data and create HA, which does sound dangerous to some, but in practice works very nicely. SSDs, I'll mention, benefit mmap v1 a lot more than these more modern storage engines like WiredTiger and RocksDB that I believe I have a few slides on briefly in this talk. Those engines were designed in a more smart way, so they just don't benefit quite as much from an SSD as mmap will, which is very inefficient. So a lot of its inefficiency is hidden with the SSD. If you're using SSDs, I would put monitoring alerts on free space at around 20 to 30% at maximum, or sorry, at minimum. Because you definitely want to keep that amount of space free because most SSDs actually do internal garbage collection and they use free space to do it. So It's being reported by some disk benchmarking, open source disk benchmarking gurus out there that using a little over 25%, or a little less than 25% free space causes the disk to slow down because it has less room to perform its garbage collection. Also keep in mind that when you have less than 25% disk space, that's not a good thing anyways, because your server could run out of disk space. This slide's really important to me because I see this a lot, which is detached block devices. This is a more common thing with other databases that don't really have good HA failover. Like MySQL, I'm not trying to knock MySQL, but it doesn't have quite the built-in failover that Mongo does. It was more common to see that remote block devices on SANS or NFS or iSCSI with that database, or also maybe Postgres. But it's important to keep in mind that Mongo has put all of these things into its own database server. It has its own HA for storage. It has its own ways to make sure that certain blocks or certain writes are more important than others. You don't really need to duplicate it, but more importantly, putting a disk 10 meters away through network switches has a lot of costs. And I just mentioned earlier, block devices are very important to databases. You don't want to make that path to data any slower than it needs to be. So the risks I want to explain for detached block devices are there's a lot more to break. I'll explain more. Block devices wrapped in TCP is slow. So you already kind of are paying a lot of price just there. Your servers usually come with good disks. At least I've worked at a lot of infrastructures where the servers already had a RAID array that's very fast. So accessing another RAID array across a network doesn't seem to make so much sense to me, especially cost-wise, if you've already paid for the RAID array that's local to your server. It's more difficult to troubleshoot, obviously, and Mongo doesn't really benefit from it. I already explained that, because it already has its own HA. It already has its own way to rebuild a member if it has no data. If you spawn up a new VM somewhere and add it to the replica set, Mongo is able to bootstrap that node also. So a lot of these technologies that a SAN is going to give you just won't really be useful, I feel. So when I need to troubleshoot a system running on EBS, NFS, or iSCSI, here's all the layers that you actually need to think about when a block device request happens. So if I'm MongoDB, if I want to request a block on a disk that's in one of these situations over a network, I first need to system call the kernel for the block. The kernel frames the block into TCP. Sometimes the frame of, let's pretend we're talking about MySQL here, 16K is the typical NoDB page size, at least when I was a MySQL DBA. NFS or iSCSI isn't really guaranteed to align itself to that exact size. So there's actually some inefficiencies there. I once worked at a system that ran an ODB MySQL on NFS, which was actually using 4K block device requests. So for every ODB page, it was actually doing 3 requests to NFS and then merging them. So lots of inefficiencies there. So let's move on. We've framed the TCP request in TCP. Now we handshake if we don't already have a pulled connection to our NFS or iSCSI or EBS. The TCP packet moves across a copper wire, which is slow, through routers, switches, potentially an Ethernet cable someone could trip over. The storage server has to parse the TCP back into a block device request, pass it to the kernel, which passes it to the storage driver, and then eventually it makes it down to a disk. So that's kind of the full path of a block device request when you have one of these remote network-based systems where, just looking over here, we would end at maybe the second, we would chop almost, I would say 3/4 of this list of tasks if the disk was local to us. So enough about that. I've definitely stressed that enough. CPUs are another one, which is important more so with the newer engines that use compression. It's important to know that the gigahertz of your CPU is less important than how many cores it has. With MySQL and Mongo, anything using a thread per connection model, because every connection creates a new thread, which is assigned to a CPU. It's better to have more CPUs than necessarily very fast ones, which will have a lot of contention when, let's say, 10 connections are pinned to that CPU. It would be nicer to say that we have 3 connections per CPU core than a really fast CPU that has, say, 10 connections. Don't quote me on those numbers exactly, but that's kind of the way you should be thinking. A lot of silly things are enabled on some OSs, like CPU frequency scaling, which might assume that maybe you're using a laptop that doesn't want its battery to run out. You probably want to turn those off for a database. Maybe that's a better, maybe an application server is a better way to save money in your data center, but usually you want your database to be pretty predictable. I would turn off anything that scales down the voltage or CPU frequency. Usually those are based on when it thinks the server is not active, but that can always not be true. So it sounds bad for the environment or for power consumption, but I would always say set your database servers to performance 100% frequency modes that are using, probably as much power as they possibly could, but that's usually where you want your power to be used is your database, because your entire application is probably waiting on whatever it's being requested. You could probably save money in other places like the application servers or caching tiers or queues or things like that. Speaking of data centers, kind of touched on this in the last one, that it's nice if you can to separate your tiers of your network so that really the things that need to access the database can, but anything else can't. If I can design a network from scratch, I usually try to say, let's have a public server VLAN where servers that actually have the need to reach out to the internet can sit in that VLAN, and the internet needs to reach them. Between those tiers, it's good to have load balancers and firewalls to your backend servers that are doing various jobs based on whatever your application is doing, web server, application server. And these servers wouldn't need to access the internet. So you'd put, like I say, the web servers or your application servers that would just proxy the response through the public server VLANs. And then the data VLAN, which is what's important to us in this talk. We'd put our databases here, and hopefully only the backend VLAN that I just will go back to in my last slide here. Would be able to talk to that VLAN. You could also put your filers here, so your NFS, if you were using it for a good purpose, probably not Mongo, and backups and things like this. A lot of servers these days have 10 gig Ethernet, or if it doesn't, it would be nice to try and get that. Not necessarily if you think you're going to push 10 gigs of data per second, but it actually has lower latency. I don't know the specifics on that. I believe it has something to do with the fact that these cards have better processors, is what I believe, but don't quote me. Just the takeaway is a 10 gig Ethernet card will have a bit lower latency than, say, a 1 gig Ethernet card. It also could have something to do with the PCI buses between them that have improved a lot over the years. Jumbo frames, if you know how that works, enable them. Jumbo frames move more data per packet over the network. Servers have supported that for a very long time, so have switches if you're using good switches like Cisco or anything enterprise. But I rarely ever see that enabled on Linux servers. So try it out. That's something to think about, because it would be strange in 2018 for your setup to not have the ability to use jumbo frames. We talked about it in the first piece of this webinar. Try to have as few servers access the internet as possible, or have the ability to access the internet. And explained it in the last talk. If someone gets into your database, they're going to try and upload it to the internet, to their house, send it home, and leave a ransom note, which happened a few years ago. So it's important to just make sure that your databases can't talk to the internet. And what I mean is, if you try to hit google.com, maybe you don't have a web browser on your server, but let's pretend you did. You should get a no route to host. No DNS name would be nice, but an attacker could always guess the IP address. So I guess my point is make sure that you don't have a routable access to the internet, so that if someone wants to upload to the Pirate Bay your database, they're going to get no route to host. The routing table can only access the data subnet. That's the end of the hardware section. And why is it so quick? It's kind of the mentality I mentioned earlier, that hardware has become a bit less important with Mongo. And Mongo is designed that you can always add more shards or more replicas. So why would you be worried so much about an individual host's scalability? Maybe you have a lot of hosts with really terrible scalability, performance, but as long as you know what that performance is and you have a way to scale it up, then it sometimes can be irrelevant how fast a single node is. And I'll just stress one more point that I didn't mention there is anyone on this call, including me, are the most expensive resource, not the hardware anymore. It's I think maybe a 1990s or pre-90s thinking that hardware was really expensive, and we'll spend a lot of time tuning the last 1% out of its performance. Keep in mind that we're expensive people for companies to pay. So sometimes don't spend too much time worrying about little things like that. And that's almost a good segue for tuning MongoDB, because unlike, say, MySQL, which I haven't used since 5.6, but it probably, I don't even want to know how many numbers of config options. Tuning MongoDB doesn't really cover as many. There isn't really a massive config file for a Mongo server with a lot of little knobs to tune. But let's go over how you would make sure that Mongo is set up properly. And quickly, let's just cover the storage engines, because that's a big part of it. mmap v1 is the default engine before 3.2, I believe. Somewhere in 3.2 that switched, or maybe it was later in 3.0. I could be off there. But the key is at some point in 3, the default changed from mmap to wired tagger, but it's still available. So this engine is a good place to start, because every Mongo deployment before, let's say 3.0, had to use it. If you didn't use a journal, or this is common with really all engines, you can lose a lot of data. In this case with mmap, it syncs to disk every 60 seconds by default. So if you had no journal, mmap will have at maximum a minute of data loss. But of course, enabling the journal protects that, and if it crashed, it's able to replay what's going on. So it's journaling, which you should always have enabled, because I just mentioned you could lose a minute of data if you don't have it enabled. Is synced to disk every 30 milliseconds. If the journal's on a separate disk, I think I'll get to that at some point here. But if I don't, it's good to store a journal on a separate disk if you have the ability to with your hardware. Or every 30 milliseconds if Mongo knows that the disk is not separate. If you use a write concern with journal true, 1/3 of the millisecond number is used for writing the journal buffer to disk. The problem with mmap I've seen in production is it fragments. So as you change data or delete data, there's holes in the data files that don't get cleaned up. I think this was kind of common with InnoDB in MySQL, but it doesn't really seem to affect InnoDB quite as much, I find. mmap is a little more random at how it stores its data. It tries to find a free space and put mmap pages in that slot. And when those slots don't completely align to, let's say, a nice number like 10, little holes are left all over the place. And the problem that happens, especially on spinning disks, is the head on the disk has a lot more scanning to do to get to these different fragmented pieces of the data. So that's something that happens with mmap. If you have fragmentation, we have some graphs in our Percona PMM monitoring, I believe, to show you that. If we don't, you can actually just use the dbstats command and look at the storage size versus the real size of the collection. And if those are drastically different, you have some fragmentation. The other engines I'll cover, WiredTiger and RocksDB, don't really have very much fragmentation because they're constantly rebuilding their data files behind the scenes. So WiredTiger is a bit more of a more advanced engine that came in the 3.0 server days. And it checkpoints every 60 seconds or 2 gigs of data changes. And with its journal, the journal buffer size, which I'll just state again before I continue, you should always have your journal enabled so that you don't have the 60-second risk unless you are comfortable with that. The in-memory buffer of the journal in WiredTiger synced every 50 milliseconds or every change if you're using journal write concern. So that's a bit more consistent than mmap. RocksDB, if it hasn't been mentioned already, will be deprecated in our PSNDB 3.6 version. I don't have too much time to explain here why, but that needs to be done. And but for now, it's still a great storage engine to be using in 3.4, and it's very easy to not get locked in with it. You can just move to WiredTiger very easily when that has to happen in 3.6. But RocksDB uses a level compaction strategy for its data files, and that's a very efficient way of storing. It's very similar to Cassandra's way of using sorted string tables on disk, and it uses different levels to compact the data down. There's some great talks on that if you want to hear more about exactly how that works. But the key with RocksDB is data is written once, and the data files are never updated after. So they're completely immutable, and there can be some duplication between the levels. So the levels are actually representing kind of a top to bottom set of changes to the data that are being compacted down to, in the diagram on the right, eventually level 4, which would be the bottom level as changes happen. WiredTiger and RocksDB have in-heap caches, unlike mmap, which just relies on a storage engine, or sorry, file system cache in Linux. They kind of rely on both of those things. They have an in-heap and they rely on the file system cache about 50-50. When WiredTiger starts up, it'll dedicate about 50% of the system memory to its in-heap cache and let the file system have the other 50%. RocksDB, oh, I went forward, sorry. RocksDB does the same thing, but Parse or Facebook actually put out a blog saying that they saw the best performance with mixed workloads at 30% in-heap cache size And what I mean there is if you have 100 gigs of RAM, you would dedicate 30 gigs to your in-heap cache, not 50%, which would be 50 gigs. Durability can be tuned for all the engines if you like. Just be careful with what you're doing there. And the commit interval and the sync period seconds can be tweaked. Sometimes I've seen SSDs benchmark with better performance when the sync period is a bit smaller, so that there's smaller batches being synced to disk. I can't get too specific on that without knowing the specifics of hardware. So what not to enable is good to know. I don't recommend you enable the CPU profiling in Mongo. I'd rather something like PMM or some kind of external monitoring worry about that kind of thing. The REST server, the HTTP server, will be deprecated soon, but don't recommend that's enabled in case there's any security problems with it. Small files is probably not good in production if you have a situation other than thousands or hundreds of little databases. And what I mean is just a lot of databases with almost no data in them, not gigabytes, but just maybe kilobytes of data. That's one use case where small files will help you. Other than that, you usually don't want to use that in production for any reason. That's just for mmap, by the way, but I would disable it in production. Same with profile mode 2, which means everything in the database is profiled. Maybe do that if you know that the server can handle it, but that probably is a little too much data than you need. The Percona PMM monitoring and the Percona tied up with the Percona server for MongoDB actually does a random sampling of queries, even if they're not slow, that will end up in our query analysis portion of PMM. So my point there is you don't necessarily need to enable profiling to mode 2, which would log everything, because if you use those two softwares together, they're already going to catch the slow queries and the frequent queries, even if they weren't slow in the profiler, without the impact of logging every single one. This slide I thought was just important to cover that tuning Linux, love your OS. Your OS is really important. The database needs it to be running just as well as itself. And this picture on the right is a kind of dirty engine, which I kind of feel I see at a lot of deployments I hop onto, where they're maybe using Red Hat, but it's 2 versions old, or the drivers aren't updated, or the sysctl.conf is just default, or they've launched an EC2 kernel and just installed Mongo and turned it on. You need to put a little more thought into that if you want to make sure things are performing to the best of their abilities. The first line I put here is I can log in via SSH, we're done. Need to think a little harder than that. Make sure the server is tuned well. So, and especially because you've probably spent a lot of money on your server, you don't want the database to be working as fast as possible. Some very nice disks at the bottom, but the sandwich in the middle of the kernel, it's just, it's not fast at all. That would be a big waste of money. If you want just a very easy upgrade, it looks like this slide didn't format very well with the very last line, but this is just a graph that Second Quadrant had a blog on about the performance gained just switching kernels, the Linux kernel, to the latest 3.10 plus kernel. So these lines in the graph that are going up are actually not from any massive change, but just the Linux kernel being upgraded. And it's just kind of a good demonstration of my point that every time your database needs to do something, it goes through the kernel, and it's a very important thing to make sure you're getting all the improvements from. Of course, let's just go back. Mongo isn't Postgres, but the workloads to the Linux kernel are similar. They're both using quite a lot of memory requests and a lot of network requests and a lot of disk. So similar things as far as use cases. In recent servers, NUMA has been introduced, which is a great idea that takes into account the locality of memory blocks. So it knows that crossing different buses to get to different chips of memory has a cost, and it actually tries to be clever and move data to local zones. The problem is this doesn't work very well with Mongo, so you should unfortunately disable that. If you don't disable NUMA and don't start Mongo in an or should I say, if you don't disable NUMA or don't start Mongo in an interleaved NUMA mode, which basically disables it, all of your memory blocks will end up on only one of these memory banks that we're seeing in this picture here. So let's pretend that let's just pick the top left. If we had NUMA disabled, Mongo and NUMA working together is going to allocate all the memory blocks to basically one node of the NUMA piece, and it's a very, you can probably see how that's not going to perform well, because if your connection lands on any of the other CPUs, they have an expense to cross over to the other side. So disabling NUMA is a great idea, just because it's required at this time, but hopefully Mongo will support it at some point. This is a command to interleave NUMA if you can't disable it. I actually lean towards using interleave in case Mongo adds NUMA at some point. I can just remove this NUMA ctl interleave all command from starting Mongo, and it will use NUMA. Transparent huge pages is a similar story. This is an efficiency tuning that was added in Red Hat and CentOS that should be turned off, and Mongo will complain if you don't. This is merging memory pages in the background to try and be a bit more clever. This might become not the case as the Spectre and I'm forgetting the other name, CPU vulnerabilities that have come out actually could benefit from using transparent huge pages, but at the current time, our recommendation is that you disable transparent huge pages. Mongo will also complain if you don't. There's some recommendations on how to do that in a blog post I'll mention coming up in here. The time source is very important with any cluster, that every node, if you ask any node what time it is, that it's the same consistent time. So use NTP, but make sure NTP is protected. There's been some security problems with or attacks that people have executed with NTP, but just make sure it's isolated. And it doesn't really matter how accurate your NTP server is as long as everyone has the same NTP source. And what I didn't add to this slide is in 3.6, the clustering actually has its own clustering time clock. So it doesn't actually necessarily care so much about the system time anymore. So I'm more talking about pre 3.6 here, that it's very important to make sure that your clustering has the same time everywhere on every node. Using NTP is basically the best way. If you're using virtualization, your system might fight with it. I've got a slide here, yep, that mentions VMware and Xen are known to fight with NTP because it has its own clock syncing. So just make sure you don't have two clock syncing systems running at the same time. Virtualizations where I've seen that happen. The Linux I/O scheduler is known to be a bad default on older kernels. Newer kernels are using Deadline, which is probably my recommendation. But older systems use completely fair queue, which assumes you kind of have a laptop or something that would be used for a lot of different purposes, not necessarily a database purpose. Deadline is a more simple I/O scheduler, and simple is good because you shouldn't be running many different things on a database server, hopefully. Try to just make sure that server X is just running just there for using Mongo. And then it's a lot easier for simpler IO schedulers to be correct because they don't really have a lot of different consumers of block devices. It's just going to be MongoDB, and it doesn't have so much thinking to do, where CFQ was designed to be a bit more clever if you were doing a lot of different things on a server or a laptop. No op is good if you have a real hardware controller with battery-backed caches, because it will usually do its own batching and scheduling. So you're basically saying, I don't want to schedule anything, just pass it down. That's sometimes a good thing with RAID controllers that are nice. This slide also didn't format the way I wanted, but disabling no A time on your block devices is an important thing to do. That's a metadata block update every time Mongo reads from a file. And no one actually cares about the access time. No A time stands for no access time. So it actually tells ext4 in this case, in my example, but your file system to not update the access time of files when they're read, because it's just not useful to the database. So you're going to save a bit of performance or bandwidth on your block device when you disable that. Just an example in the screenshot here. So the defaults comma no A time in the file system options disables no A time. Block device read-ahead is another tuning that is often not tuned very well on a system. I recommend that you turn it down to 16 kilobytes or 32 sectors on most systems, so that Mongo can worry about how to be clever about caching blocks. The risk here is if you don't do this on CentOS 7, I've noticed the setting is 2048, not 32, but 2048, which means that many sectors will be read ahead of any block request. So you're requesting quite a bit of data every time you hit the disk. I think 2048 would actually be 512 kilobytes. So if you just needed an 8 kilobyte piece of data from the disk, let's pretend 512 is going to be fetched into the file system cache, and that could be completely useless to Mongo potentially. So that's kind of the risk you're avoiding by turning this to a very low number like 32, which is 16 kilobytes if you have 512 sectors on your disk, which is basically always. Changing this can be done in your udev config. This is also in a blog post, but this is a file that your kernel will read on startup and apply the change. Also in this example, I'm applying deadline as the queue scheduler, if you notice in the center of the line there. Tuning Linux, virtual memory is an important thing to do. Depending on your memory size, Linux will default to a setting I think is a bit too high. Dirty pages are basically pages that have been changed but still needing to be written to storage, and the kernel will by default allow a lot of dirty pages into memory until the commit interval that it needs to be flushed. But also there's some other ratios called the dirty page ratio and the dirty page background ratio. And 30% can be a bit too high on really high memory servers, because 30% of, let's say, 100 gigs of RAM is 30 gigs. And I would rather have that dedicated to Wired Tiger or the file system cache than dirty pages, and just make sure that Linux cleans those up faster. So the way to do that is actually reduce this default number of 30 to something closer to 10. So that at maximum 10% of your memory can be used for dirty pages, and Linux will be forced to clean that up faster so that more memory is available to the database. I hope that made sense, but I can't speak too much more about how that works, but my blog post on it will explain it a bit better. The background ratio is similar, but it starts earlier. So you usually want to set that, well, you have to set it lower than the previous value. So I usually recommend 3 for your background ratio so that the cleanup starts in the background. It's kind of a soft limit at 3% of your memory usage, and going back at 10% of your memory usage, there's a hard limit that says we can't do more than that. We have to flush this data to disk. And that's just a common theme here is Linux has a lot of jobs to do. So this 30% value is probably a great default for a lot of different use cases. Raspberry Pis use Linux. All sorts of things use Linux. Phones, Android phones, I believe. So keep in mind Linux has a lot of jobs to do, but we're asking it to do a lot of work with a database. So we need to tune these things a little smarter than defaults like 30. And the default for the background ratio is 15. Swappiness is another great one to tune. The default is 60. That's good for slower things. Servers that are a database, I'd recommend 1 is used. And there's a blog post that Percona has on why 1 is probably a great idea instead of 0. And if you want some disk-based swap to happen, maybe you have really fast disks and you would rather have that RAM used for something else, maybe 10 is a good value, but I would use 1. And that's just shown in the bottom right example here. Ulimit is a limitation in, or kind of a resource limitation in the Linux kernel that doesn't let programs use too many threads or too many open files or too many CPU seconds, things like this. This is one of the most common problems I see with Mongo is the number of user level processes is set too low. And if I could actually ask a question and get an answer in a room, I would have asked who knows why that's important, but I'll explain because everyone's on mute here, that every connection in Mongo actually creates a process. So the user level process limit is actually very, very important and basically needs to be larger than your number of max connections for Mongo. So the user level processes in Linux usually defaults to 1024 per user. So the user running Mongo usually can only open 1024 processes, which really means you can only have about 1,000 connections open to Mongo if you don't tune that. Same with open files. Mongo opens a lot of files, and that limit can be pretty low on Linux. So I recommend there's 64,000 open files allowed on a system that is using Mongo as a good start. It's unlikely you'll ever hit that, but I don't recommend you use unlimited because if Mongo has some kind of bug that freaks out, it's better to stop it early than set that limit to unlimited and let it take down your whole server. For the previous value I mentioned, user level processes, I would set that to something as high as your maximum connections, or maybe 32,000 is what I'd recommend for that, but definitely not the 1024 default that Linux has. You can set your ulimits in securitylimits.d on Linux or in a systemd service init script. And here's the good news. If you use our RPM, which is for Red Hat and CentOS, the Percona MongoDB packages are already doing this. Potentially the MongoDB Inc. enterprise binaries too, but I can't say for sure. So this is just a screen grab of our GitHub showing that we're setting limit no file and nproc to 6400 each because we feel that those are good values. Here's a good starting point for your network stack. A lot of Linux tunings for kernels default to kind of the days when 100 meg internet was more common. These are some I suggest that will also be in the blog, and I'll move on because we just have about 11 minutes left here. And this is the blog that I'm talking about that covers a lot of the tunings that I said, just like on the last slide, that the blog will explain in a bit more detail in case I bore people. But yeah, look at this blog. This kind of explains what I would recommend in more detail, and more so a justification of why, because that's kind of important, not just copying and pasting what we think is are good values. After I wrote that blog, I realized that there's a lot of different tunings you need to do and a lot of different files that you have to touch to pull that off. Luckily in Red Hat 7 and CentOS 7, I'm not sure about other OSs, TuneD came out, which is a Python daemon that can read kind of nicely formatted files and apply performance profiles to servers. So I think the link is right here, underlined in blue at the bottom. I wrote a TuneD profile for MongoDB and put it on our Percona lab repo that applies most of the tunings I just covered on a Red Hat or CentOS based system. So the really cool thing is you can just clone that GitHub and run basically one command and have most of the tunings that I've recommended here set up. It can't tune NUMA, so keep that in mind. TuneD doesn't have access to do that, so you need to make sure NUMA is set up right, as well as the file system options and the file system itself. And I'm not sure if I mentioned that earlier, but if I didn't, that you should never really use ext3, and if you're using WiredTiger, ext4, because of some instabilities. ext3, the reason why I say that for any storage engine, I don't recommend ext3, is it can't allocate files, pre-allocate files very quickly. For ext4, WiredTiger and ext4 are known to fight each other, so I recommend XFS is used usually with Mongo, unless you're not using WiredTiger, then possibly ext4. But the TuneD can't tune those things, so you have to do that yourself. Same with, actually no, that should be it. So NUMA and file system type and options can't be tuned by TuneD. The rest will be. So that's a nice shortcut. So the last piece of this talk is going to be on May 3rd, 2018, 1 week from now, at the same time slot as we are in now, for 1 hour. And with that, we've got about 8 minutes left for questions. So I'll put it back to Emily for that.
Thank you so much for that, Tim. Go ahead and enter your questions down in the questions panel. We'll take time to answer as many questions as we can. As a reminder, we'll do a full blog post for anybody who has questions that we couldn't answer in time. All right, so our first question is there a benchmark on performance improvement achieved through these turning versus like without them? Tuning. I can't talk today.
Not something that we've officially published, and that's, I guess the best way I can put it is something I have as a goal in mind to do, but not at this point. Not something that we can publish and stand behind any criticism yet.
Okay. I was thinking we have a couple of things on our blogs on PMM. PMM would be able to show on your own instance, wouldn't it?
Yeah, well, that's a good point. The danger with benchmarks is the environment can be simulated wrong, or it just doesn't fit your use case. So, of course, it's a tired old thing to say, but it's always better to just test on your scenario. And like I mentioned earlier, Mongo can be deployed in a lot of different ways, mostly because hardware hasn't become so important as other databases. So you could really deploy it even on really slower hardware or fast hardware. So it's more difficult to just kind of benchmark a singular system. But yeah, a goal I have is at least to have within a defined singular environment, a before and after. And that's definitely a goal I have for 2018.
Thanks, Tim. Well, we'll stay tuned for that. So it looks like we are actually doing pretty good. I'll take a pause for a couple minutes just in case there's any other questions that come through. And then, Tim, did you cover part 3? What's going to come up on the next one?
No, I didn't. So let's flip back here and just quickly mention what's in part 3. So part 3 is going to cover, I don't have a slide for this, but troubleshooting different problems, usually performance related if your server is working, but also places that you could look if your server is not working and maybe you're just setting up for the first time and there's a permission denied or something. Where would you find that? Schema, I think we'll touch on quickly, but that gets too large to talk about sometimes. Data integrity. So keeping in mind we're talking from a kind of a perspective of someone who maintains a production for MongoDB, not necessarily a developer. Data integrity would be kind of the checklist that you as a DBA would check off when you're going to say, I'm going to be responsible for holding the pager for this database application. So we'll look at different ways that you would make sure that this system is going to have data integrity on different failovers, stuff like that. And scaling reads and writes, which you might already be able to kind of guess how. So I'll just say it now that will be through sharding and replication members, 2 ways of scaling reads and writes. And actually, there will be a mystery kind of third option for scaling reads and writes that maybe you haven't thought of.
Oh, I like mystery. Okay. Well, we'll stay tuned for what that secret, extra a little bit is going to be. Let's see. Our next question is there a note that talks about setting up incremental backups with the help of a hidden replica set secondarily?
Incremental backups, no, but I can quickly talk about how you would do this and how that support is at some point coming to our backup tooling called MongoDB Consistent Backup. First, just to recap, a hidden secondary is a member that can't win an election and is kind of just there for backups or maybe some very expensive job you want to run that your application just can't be affected by. It doesn't read from, it doesn't write from this node. So taking backups in an incremental scenario doesn't exist in our Percona backup tool today, but let's pretend it did. The process that would take basically is a full backup of the data would be taken every so often, maybe once a week, maybe every 3 days. Other than that, you would back up the op log only any other day or every hour or any points in between as your way of getting an incremental backup. And if you wanted to restore to an exact point in time, you would replay those op logs to the exact point in time that you wanted to restore to. So that's support that we have planned to add to our Percona tool, but it's not ready yet. And unfortunately, I don't have an exact ETA for that, but it's definitely in the plans. But if you wanted to pull that off yourself, how I would do it is kind of how I just mentioned it there. Choose a backup option of your choice to perform the full backup. And secondly, choose a second option that's going to take the kind of snapshots of the op log and store them. And hopefully pretty soon we will have a supported or at least beta supported tool that will do that for you.
So Tim, I mean, I guess while we're waiting, for that update, I mean, is there any third-party backups that you know of today?
Not in the open source community specifically. Unfortunately, that's something that's kind of left to case by case automation right now. I've seen one project in GitHub that had some promise. I'm actually forgetting the name of it. Possibly, I could find a way to actually put that somewhere if I remember it. But currently, no, there doesn't seem to be any kind of strong players. I'm not trying to toot our own horn at Percona. Aside from our Percona backup tool, or using MongoDump, or enterprise tools with MongoDB Enterprise that you would pay money for. Yeah, so I guess that's a good point to mention, if I didn't already mention it about backups, that our Percona backup tool is an open source project. And if any other organizations want to collaborate or have the resources or just really the priority that means we just have to get the incremental feature now, talk to Percona and or even send code our way on GitHub, because we're definitely willing to accept pull requests in Python. I should have mentioned that it's a Python project.
That's a great point. I'll sneak in one more question and then we're going to wrap up. Speaking of MongoDump, does it lock while it backs up?
Not unless you specify it to. So no. It does basically a fairly lazy backup. And here's something that's important to mention is it is a lazy backup tool unless you specify the oplog flag. So I think that's actually similar. Actually, no, that's different in MySQL, where when you do a MySQL dump, you usually have to add your slave info flags. But a little different here is in MongoDump, there's a separate flag called oplog that will dump the oplog while the backup happens. None of these things lock, but I'm just mentioning it, that both the lazy backup operation and the dumping of the oplog don't cause any locking. The reason why maybe you're asking this question is I mentioned a hidden secondary as a way to avoid impacting your application when you perform a backup. Maybe that's why. The reason I say I would dedicate a node for backups is more just for the CPU and disk resources not being affected than locking. You could actually MongoDump any node in your system. It's just going to add CPU and disk and kind of slow the system down. It's not actually going to lock anything. Yeah, that's the best way I'll put it.
Okay, and then just making sure will this lock on collection or on the database, or can it do both? Did I stump you? Sorry.
Could you say that one more time, Emily?
So when we're talking about MongoDump and locking, so can it lock on collection or on the database, or both?
That's actually something I haven't thought about. That's something I might need to get back to you on. But I think the key is you don't really need to lock on anything. But I guess maybe there could be a use case that I haven't thought about. But the efficient way to do the dump would be kind of like I mentioned, using the oplog flag and just not using locks, because the oplog flag is actually dumping the oplog in a chronological order, so that that consistency is gained there without needing the locking, basically.
Okay, that helps. that answered the question. Thank you so much, Tim. All right, well, with that, we're going to conclude today's webinar. Thank you so much, everybody, for tuning in today. A recording of today's webinar and the slides will be sent along later today. And we hope to see you on part 3, which will be coming up in May. Details will be uploaded to the site probably, hopefully, by the end of this week. And an invite will be sent out as well for that. Thank you, Tim, for presenting today. We learned so much.
Thanks, everyone. Thanks, Emily.
Bye.
Bye.